So please help me welcome to the stage Meredith, Patterson.
Thank you all so much. It's fantastic to be here. John kind of stole my opening. I was going to poll the audience and ask who doesn't get to program in a functional language at work. Okay, that's actually most of us. All right, yeah, I'm stuck in Java and C++. But what I'm going to talk about today is C. So, just to introduce myself briefly, my background is in linguistics. I got poached into a computer science degree at the University of Iowa with a formal language theorist, and then I kind of tripped and fell into security. This ended up evolving into the field of language theoretic security. We just had our third IEEE workshop on Thursday. And parsing is basically my favorite thing in the entire world. So why do we parse things? Well, when we have a stream of bytes that represents something, we want to know what it represents, and parsing is how we turn that stream of bytes into an object that we can reason about, an object with some semantics. When we have an object and we need to send it somewhere else, we can serialize it into bytes and we can reconstruct those. Now this turns out to have some interesting security implications. As Taylor Hornby said, the illusion that your program is manipulating its data is powerful, but it is an illusion. The data is controlling your program. And if you step back for a second, this makes sense, right? Because what's going to be driving what your program does? People are going to be sending input to it, and it's going to do different things based on what that input is. And if it turns out that there are squirrely edge cases that you didn't consider, well, your program's behavior may end up being undefined. And it turns out that even when you can't work in a functional language, being able to use functional idioms anyway helps you to write code that you can reason about much more effectively. Now on the security side, LangSec has a couple of slogans that we like to use. I'm only going to hit on two of them today. We talk about shotgun parsers, where you mix the logic of your input handling with other logic, allocating memory incrementally. This often leads to buffer overflows. So if you have some input that you're going to do something with, if you can, like if it's not a streaming or incremental input, it is ideal to recognize that completely before deciding what to do with it. Furthermore, if your input has some kind of definition to it, if you could describe it in BNF, you had better. And moreover, your implementation had better implement that grammar, otherwise the implementation is just wrong by default. One of the things that we've discovered in the last 10 years or so is that when two implementations speak slightly different dialects of the same protocol, those implementations may be mutually intelligible in most cases, but it's possible to find edge cases that allow you to do things like forge SSL certificates. And there are plenty of other bugs that have cropped up just in the last couple of years that are fundamentally parsing vulnerabilities. I'm hoping that named vulns with logos have jumped the shark at this point, but the one that kicked that off was Heartbleed. That was absolutely a parsing vulnerability. There was supposed to be the length of the length specified in the heartbeat packet and the payload were supposed to be identical, and if they were not, you could craft a packet that would leak the contents of memory, sometimes including key material, back to the attacker. Shell shock. That was just a straight-up bash parsing vulnerability. Ghost. Back in January, get host by name in glibc turned out to have a buffer overflow in it if you sent it a maliciously crafted network name to resolve. And image tragic. There was actually a talk on that one at the LangSec workshop, and that video will be on YouTube fairly soon. Again, just a bog standard parsing vulnerability. These kinds of things should not happen. I mean, if you look at any RFC, skip to the appendix and you'll find a BNF definition. But people hand-roll parsers because that's what we've done all along, and they end up with subtle variations that lead to mutually intelligible dialects. Now, in functional programming, there are a couple of principles that we like to try to preserve. Soundness is one of them. We want to make sure that every answer we get back is true. If we get an answer, it should be true. Completeness. For every input that you can send, if an answer exists, it will be returned. And totality. Every execution will terminate, and moreover, there will be exactly one output. And these turn out to be extremely useful principles for security as well, because they enable you to reason about the states that your program can be in, and therefore avoid edge cases. So, I'm going to really briefly go through some fundamental parsing concepts, and then we're going to move on to the library I wrote. Okay, so this is a sort of cut-down version of the Chomsky hierarchy. There are actually, in each of these 4 classes of grammars, there are actually fun subclasses and lots of fancy algorithms you can get into to apply them all. But in general, the regular languages are equivalent to regular expressions. The context-free languages are equivalent to push-down automata. Take regular languages and allow them to recurse back on themselves. The context-sensitive languages are equivalent to linear-bounded automata, which are basically Turing machines with a finite tape. And then recursively enumerable are just your full-on Turing-complete languages. Okay, so let's talk about kinds of parsers. Recursive descent parsers are, the old classics. Back in the day, everything was written with recursive descent parsers, and in fact, you will still find recursive descent parsers in many, many, many Unix daemons that we rely on today. If you've not read Jack Crenshaw's tutorial on writing compilers, it is fantastic. I strongly recommend everyone play with it. It's hilarious too. Problem with recursive descent parsers is that if you have a grammar that is left associative, you're kind of up a creek because they'll never terminate. Also, there are sometimes pathological cases where you end up with exponential runtime, and that's no fun. Okay, so Brian Ford came up with parsing expression grammars, which visually are extremely similar to context-free grammars. They are always unambiguous, and you can have tokens of look-ahead. However, left recursion still doesn't work. Now there are also packrat parsers. Packrat parsers are basically just memoized pegs. And the awesome thing about them is there are a couple of approaches for trying to handle left recursion. They can't all handle indirect left recursion, where a rule doesn't immediately reference itself, but A references B, which references A. That can sometimes be an edge case. And nobody can really quite agree on which implementation has the fewest unpleasant edge cases. So packrat parsers are not hugely widely used. The ones that people use more often tend to be parsers for context-free and regular languages. So LLK, that's left recursive CFGs. LALR, which was written by Don Knuth, also context-free and recurses to the right. GLR is a generalization of LR. Instead of yielding a single parse, though, you can get a parse forest back if there's more than one possible parse for your for the string you're parsing. There are also so one of the funny things about regular expressions, PCRE decided to introduce recursion, and now everybody kind of just assumes that regular expressions are going to have weird pathological cases, and this is wrong, because by introducing recursion, PCRE went and made itself context-free. However, Ken Thompson, when he was working on grep, came up with the NFA to DFA algorithm and a virtual machine, basically, for processing regular expressions, which is actually that small. Like it only has the power of a regular language. It does not extend up into the context-free languages. Now, one of the interesting things about Hammer is that it's able to parse binary formats as well as just character-based formats. Parsec and attoparsec and Bison and just about everything else is focused on character streams because, you know, initially parsers were mainly part of a compiler. And if you're using high ASCII to write your if you're using high ASCII to write your source code, I guess you're working in AGDA. But so nobody has really focused on trying to do this well, and thus there just aren't really any tools for it. Furthermore, what happens if you have to deal with weird endiannesses? Again, nothing really pays attention to that. It is possible to coerce Bison to do binary parsing. But unless you're writing an interpreter or a compiler, Bison's interface is just abysmal to use. And unless you have nice byte alignment, which not every protocol is going to give you, it's a pain to deal with, with bit fields like flags and stuff like that. So let's talk about what we want to achieve in designing a parser combinator library in C. So we're going to assume that people are going to try and use this in threaded things because people love to thread stuff in C, despite how awful pthreads is. So we want it to be thread safe. We want it to be reentrant. We want the API to be easy to understand. We don't want to confuse people. POSIX compliance is just simply polite. Speed is useful, but above all, it needs to be correct. C presents us with a bunch of different obstacles on this front, and we're going to go through those now. First of all, it doesn't really have much of a type system. Like, you're not going to have higher kinded types. Basically, you get primitives, you get structs, you get pointers, and that's about it. However, even if the compiler doesn't know anything about it, you can still define semantics for the types that you're going to use. And you can reason about those yourself. Yes, that means you're doing the hard work that the compiler should be doing for you. That's why we have better languages. But if you're stuck with C, you get to do the reasoning yourself. But this is possible. A slightly more practical problem is that you can't just hand functions around. So, like in Parsec, which is the Haskell parser combinator library, it's just trivial to define a function and use it as an argument to something else. In C, we have to use function pointers. This is clumsier, but it works. If it were C++, we would use functors, and we'll actually see a little bit later we're going to use something very like a functor. But I'll get into that in a little bit. Another nasty problem, strict evaluation. Haskell's lazy. Laziness is wonderful. Laziness lets us do all the things. Laziness lets us do things like declare a parsing rule that refers to itself in one line. We can't do that in C because we can't reference something unless we've declared it. However, we can forward declare it. So it adds an extra step, but it's still doable. Tony Hoare's billion-dollar mistake. Null pointers. Well, those are something we can't really escape in C, but we can handle them. The first step in handling them is to tell yourself what they mean. And in our case, null, we decided that null is basically going to be the same as none, right? So if your parser fails, it does not return a result. That's like returning none. It returns null. The real solution is you have to do that in a whole lot of null checks. And there is basically no way around that. And I am sorry about that. But, if you can avoid using C, try. C has no garbage collection. You get to manage your memory all by your lonesome. And this is something you want out of a systems language, but it's also really annoying because if you're going to be relying on malloc, that means that you have to free things yourself. What if you don't know where everything's going to be? How much of a recursive nightmare is it going to be? Yeah, we just decided to punt that problem with a custom allocation strategy. We're using an arena allocator. So for every parse that you execute, you're just gonna the allocator will carve off a chunk of memory. It will do everything in the context of that chunk of memory, and when it's done with that parse, it destroys it. Just kills the entire block because that's easy. It's also possible to add additional allocators. We've had that happen already, and I'll talk about why. Another problem. How are you going to do method dispatch in a language that only has functions? vtables. I used to assume that vtables were hard and confusing and stuff because I learned C++ and it's that scary up under the hood stuff that that only the real gurus understand. But actually, vtables are really easy, and we're gonna walk through them a lot. All right, so let's talk to Hammer. Hammer has a parser combinator front end, so you're basically just composing functions together, rather than writing rules that you then have to go and remove conflicts from. It has 5 different backends: PackRat for context-sensitive languages, LLK, LALR, GLR, etc. for the context-free languages, and a variation on the Thomson regex VM for regular. We also have scads of language bindings, like Python, Perl, PHP. Somebody keeps asking about bindings for Haskell, and I can't figure out why. But you can use Hammer from quite a lot of other languages. Runs on Linux, runs on OS X, recently got it working on Windows thanks to a contributor. Okay, so just to give you an idea of the naming conventions we use, all of our named structs, the types that we use start with an uppercase H and we camel case them, and then functions are using underscores. This just helps kind of visually separate things because, like I said, if you're creating an idiom, you kind of get to fill in all the little details. So you can do whatever is easiest for you to be able to keep track of what's what. We chose this because it was easy for us. So here is a cut down, super simple example of a parser and using it. So in the main function, so haction is one of our combinators. I've got the var thing there just because there will be other combinators going into that. And then a function pointer that will be applied to the results of a successful parse. Parsing it, excuse me. Right, so after you've done that, there's a single function you call. You will get a struct in your result. You can pull it out, do something with it, and that's it. You don't actually have to do any of the cleanup. That all gets done behind the scenes for you. So let's take a closer look at the various types we're going to use. We have a lot of different parsers, and all of them are just instances of this struct. The struct contains a vtable, which we will explore later. The backend is just a local flag to indicate which backend are we using. Backend data is just a place where we stash things like parse tables or first and follow sets or anything that the backend might need to use as part of its own machinery. The end pointer is kind of a catch-all. If this combinator needs it needs to be instantiated with some information, we're going to stick it there and pull it out later and use it. For instance, if you're parsing a token, then the token to match against will get stashed in the environment pointer. Desugared we'll talk about in a little bit. We have a couple of function pointers that, a couple of types of function pointers that get applied to to parsers and their results. If you need to use a semantic action, that's what haction is for. It transforms an abstract syntax tree into something else. If you're familiar with attribute grammars, also from Donald Knuth, that's what inspired the hat or bool combinator and the predicate function. If for some reason you need to say like check consistency between values in your parse result, that's what this is for. Like in the case of Heartbleed, for instance, like if the actual length of the payload needs to be the same as what the packet claimed the length was, then you could use a predicate to check whether that's actually true. And if it's not true, it would reject the invalid packet. And oh my God, we have monadic bind. That had to get introduced for a situation where we had a stack of protocols, like 3 protocols. The first one spits its output, the output of the first one becomes the input of the second one, the output of the second one becomes the input of the third one. This is what bind is for. Bind is for chaining things together, just like was discussed in the monads are not burritos talk. And we've got some result types. A parse result is an abstract syntax tree of tokens. It also gives you some stats on how much did you parse, and it hangs on to a reference to the memory context until you destroy it. And then the tokens themselves, it's basically a tagged union, and we've defined some basic token types like sequences or strings, well, octet strings, integers, but you can also define your own, which is particularly useful when you need to chain combinators together with bind. All right, so let's take a look at some of the actual parser combinators that we've got. So we have a boatload of primitive parsers. These are ones that correspond to a leaf node in your in the abstract syntax tree of whatever you parsed. So character, token, range of characters, not in some set of characters, and the arguments like C and stir and lower and upper, those just get banged into that end pointer that we saw earlier. We also have parsers for integers, both signed and unsigned. You can parse an arbitrary slice of bits of however many you need. You can match things in a range of integers. It's also pretty useful to be able to match end of input. Not every language requires this, but when you need it, it's pretty much essential. So we've got a bunch of ways to combine primitives. The two that you'll see most often, are sequence and choice. You want to be able to line a bunch of parsers up and just parse them and apply them one after the other. And it's also useful to be able to say either this combination of stuff or that combination of stuff. We can repeat things. We can do it 0 or more times. We can do it 1 or more times. We can do it exactly n times. And we can also flag a parser as optional. So you'll notice that all of these take some amount, some parser or parsers as their arguments. So for optional, for instance, optional is basically saying it's basically the Kleene question mark from RFC BNFs. Sequence and choice are using varargs. Those are variadic. You can line up as many other combinators as you want to or need to. Of course, because it's C, there are varargs. Vararg lists have to end with null, and it gets kind of ugly in compilation if you forget to do that. More ways to combine things. Ignore lets you match something, but then just not bother to put it in the parse tree. If you don't need to keep it, then why bother? And we've got some interesting higher order combinators. Length value is probably the most useful when dealing with network protocols because it's very, 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 very common to see a length field followed immediately by some payload. And when length fields are not immediately followed by payloads, this gets super messy. But fortunately, in most network protocols, we're able to do this. Boolean and, Boolean not. And then here's how we do recursion. So if I need a rule to reference itself, I declare it as an indirect, and then we've got a bind indirect function to complete the circular reference once the parser has actually been defined. We saw a chatter bool a little earlier when we were looking at the predicate function. This is what validates results. Semantic actions, same kind of deal, and monadic bind. And then there's the weird things. So, anybody ever looked at TIFF? The first 2 bytes in TIFF tell you what the endianness of the rest of the file is. We had to implement a combinator for that. I mean, because we had implemented endianness as a feature of the input stream, and so if you need to change that up on the fly, you basically get to go and reconstruct the input stream behind the scenes. But this will do that for you. And then, I mentioned long distance dependencies, things where like the length of something and the payload of which that is the length are not right next to each other. There's really no clean way to to store that value, that initial length value that you parsed, but you could stash it. So we made a symbol table. I'm really sorry. It actually says, like in the docs, please don't use these if you can possibly avoid it. But we have run into protocols that we had to use this with, and we will see one of those in just a little bit. But first, let's look at something simple to put this all together. Let's look at DNS. This is actually going to be kind of a cut-down example. But at the top level, a DNS message consists of a header, 0 or more questions, 0 or more responses, and then we're done. If there's anything beyond that, it's invalid. You don't want to have extra crap tacked on to the end of your DNS message. So you'll notice that we've got an action chain with an outer rule, and then the sequence of these 4 things. Validate DNS is incidentally, this example and the rest of the code that goes with it are all in that repo. So you can follow along if you want. So we've got a validation function which checks it does some sanity checks on the sequence that got parsed, and then if that sanity check passes, the semantic action will pack will take the parse token and put it into an actual DNS structure. Let's take a closer look at what DNS questions look like. Well, we've got a sequence of a queue name, a queue type, and a queue class. I've got other rules defined for queue type and queue class. Queue name is pretty short, so we just did it in here. It's 1 or more of, and now there we've got the length value combinator. So what this is saying here is you will parse somewhere between 1 and 255 unsigned integers. And then at the end of that there will be a null byte. The resource records are also similar, except they will be up to max unsigned int 16 octets. Uint 8 is just an octet. And then the validator function, so this gets a little hairy again, kind of because it's C and we have to dereference things manually. So we saw earlier at top level, that a sequence is the top level of the DNS message. So we want to make sure that really is a sequence, right? If for some reason the top level token, the root of the AST is something other than a sequence, this is just wrong and cannot possibly be a DNS message. So we dereference all of the, we dereference several of the fields that we parsed, and then we make sure that what we parsed actually checks out with what we expect. And if any of those expectations are violated, then the validation fails. Otherwise, we return true. So let's dig a little deeper and take a look at how this is actually working up under the hood. Step one, write as little code yourself as you possibly can. So this is basically how we declare combinators. You'll find this in hammer.h, the header file. So what this does is, we've kind of got there's some interesting memory machinery going on behind the scenes, like we talked about, custom allocators. Some of our combinators have no arguments. Some of them have a fixed number of arguments, and some of them can be variable. So what the macro at the top is saying is that if we're declaring a combinator that takes no arguments, like uint 8, for instance, that macro is going to generate a declaration of the combinator function itself, and that __m concatenation there. You'll notice that it takes an H allocator as an argument. This is kind of easier to understand here. So anything with an M tacked onto it, that's saying it's going to be using a custom allocator. The V functions are for when you're actually using var args, and the A functions are when you're passing an array of other combinators around. So what this ends up doing is you declare your combinator by return type and name, and it's going to generate function declarations like these, depending on what the signature is, and then you have to go and implement them. But at least this makes sure that everything will at least be declared, and the compiler will warn you if you need to, or the compiler will tell you if you need to go and define it. Okay, so how do we get from a stream of raw bytes to a parsed thing? Well, we start with octets. The base, the type that we expect as input is a pointer to uint 8t. We want a big old stream of octets, and internally, the input stream is going to keep track of where it is. Where are we in the index is where we are in the stream itself. Length is how long it is. Bit offset is what we use when we're doing things in a non-byte aligned way. So, if you decide to, if you've got a protocol that has 3 bits worth of flags at the very beginning, and then just starts dealing with octets, the bit offset will keep track of where you actually are in each byte, so that so you don't end up accidentally parsing some of the same bits twice. So this is kind of the top level parsing function that we have. And you'll notice it's got one of those, it immediately punts to a function that takes an allocator. Now you'll notice that we're passing it the system allocator, which is just, malloc and all of that. It's basically a struct that has pointers to like malloc and free, all of that. So what does it do? It sets up the input stream, and then it punts to the vtable. It just immediately looks up which backend is the parser using. Okay, use that parser function. So what do these vtables look like? Well, here's the one for PackRat. All vtables are required to implement compile, parse, and free. All vtables are all backend vtables are required to declare these rather. In PackRat, compilation is no-op. We don't actually have to do any kind of preparation. We can just go. We don't have to generate first and follow sets or parse tables or anything. So let's take a look at that parse function for PackRat. And I've removed a lot of the boilerplate here. This is kind of the interesting part. So the very first thing we do is we create an arena using the arena allocator. We carve off a big slab of memory that's going to be the context for this particular parse. And if something bizarre happens, if something unexpected happens, while we're parsing, we have some machinery to clean up the memory that we allocated rather than just leave it leaking. So, in order to keep track of the state of the parse, because PackRat has, with all the memoization, there's a lot of stuff going on that needs to be kept track of. So we allocate a struct that deals with all of that state. We do the parsing using using PackRat's local, using its low-level parse function. We tear stuff down. If we didn't get a result, then we free up the memory, and then we're done. What's going on in this hdo parse function is basically just worth recursion. That was the first left recursion supporting algorithm for PackRat. And so we encapsulate all of that in one function and the things it calls, and the only objects that get manipulated are the parse state and the result. Nothing else gets touched, and so we don't have any other side effects. The goal here is to localize everything that's going on within the memory context that we carved off. So what if we want to do something context-free? Well, we'll look at LLK. LALR is not too different, and so in the interest of time, we're only going to look at LLK. So there's some sanity checking that starts at the beginning of the compilation step. So what's going on here? So we have a parser, right? But it's a tree of combinators, and that's not something that that's not something that that LLK or LALR were ever really intended for. We need to figure out a way to translate the tree of combinators into something that either one of these algorithms can use. So we desugar it. First and follow sets for LLK, parse tables for the LR ones. If we transform the tree of combinators into a sum of products representation, basically a sequence of choices, then we can turn that into first and follow sets or parse tables. So the way we do that is we start at the root of the H parser and we start walking the combinator tree, just changing, or transforming the combinators that we run into their sum of products equivalents as we go. Then once we have the sum of products representation, we go and generate the first and follow sets or the parse tables, whatever we need to do. And we take that and we bang that into that void pointer backend data that we saw earlier. What if we're doing a regular language? Well, we walk the combinator tree again, but instead of translating into a sum of products representation, we just translate it directly into instructions for a regex virtual machine. And again, we just bang that into the backend data pointer, and then we go off and use it later. And this is basically a tiny little compiler. Like, I always thought it was going to be hard to write a compiler, and turns out if you translate instructions into other instructions, that's pretty much what you're doing. Okay. Sorry, I screwed something up. Okay, yes, so this is a question that we haven't really touched on yet. Because we were saying, okay, well, we've got these combinators, some of them we can use in some of them we can use in some backends, but we can't use every single one in all of them. Like indirect, for instance. It is not possible for a rule to recur on itself in a regular language. So you can't use the indirect combinator if you're using the if you're using the regular backend. But how does the program know? Well, we can't introspect, but we can have the combinators tell us. So this is the vtable for the character parser. You tell it what character to match, it matches just that character. So all of the parsers, you will find a vtable like this in all of the parsers. They will have a function that packrat uses to parse whatever that combinator parses. Then they'll have a couple of function pointers that return Boolean, one of which asks, is this valid to use in a regular grammar? And the other one asks, is this valid to use in a context-free grammar? And htrue is just a function that we wrote and can therefore reference that always returns true. How about many? Well, whether it's okay to use a 0 or more parser, 0 or more of something parser in a context-free or a regular parser depends on what that something is. So the definition of this combinator points to functions defined in the implementation for that combinator that look at the children. So many of some other parser. Well, is that other parser valid regular? If it is, then so is this. Ditto for context-free. And then for something like length value, which you can only use in packrat, hfalse is the equivalent of htrue, but returns false. If you can't introspect on it, you can still have the thing that you wish you were introspecting on. You can just implement something that will tell you. We don't have RTTI in C, we don't have reflection in C, but we can put in the missing machinery that the language doesn't provide for us. Okay, so let's take a look at a real protocol and a particularly ugly one. This is DNP3. Well, this is a high-level overview of DNP3. Actual DNP3 extends to several hundred pages of PDF. What is DNP3, you ask? DNP3 is a SCADA protocol. It is used in industrial control systems for things like keeping power plants running, keeping dams working, keeping phone systems running even. And it's 3 layers deep. This is what we had to introduce monadic bind for, because we need to be able to take a look at the link layer, get the payload, pass that up to the transport export layer, parse it, get the payload, pass that up to the application layer, and then do something with it. So we have to chain them together. But it gets uglier. So diving in to the header a little bit. This doesn't look so bad to start, right? I mean, this looks almost regular, right? Because this is just saying a sequence number followed by flags followed by a function code. This is saying an optional prefix followed by some object data. And, one follows the other, right? It'd be nice if it were that easy. Because in the text of those couple of hundred pages of PDF, they describe all kinds of semantic dependencies between these different pieces of the packet. And so it's okay, right, for flags and function code to, those are adjacent, right? You don't have a long distance dependency there. But what about like group variation, like the tuple of group variation, even worse, and all of the objects? Those are nowhere near each other. So that's what we had to use put value and get value for. We have to stash all of that. So yeah, we had to add the symbol tables simply because people can't write protocols safely. And this is what happens when a bunch of vendors of like power system hardware get together and everybody wants their special features to get in there. We end up with just absurdly insecure protocols because they are so complicated that it is nigh impossible to implement them correctly using traditional methods. So we did it using parser generators. It took a couple of months. Sven Moritz Hallberg did this pretty much all by himself. And the next question was, did it actually work? Did we achieve anything this way? And we figured the best way to find this out was going to be to fuzz it. So Michael Zalewski at Google has written a absolutely amazing fuzzer called American Fuzzy Lop. It's named after the rabbit. And you compile your code with a wrapper around Clang that American Fuzzy Lop provides, and it instruments the binary, and that works hand in hand with a genetic algorithm-based input generator. So it basically generates inputs, looks for state changes somewhere in the program, and if it finds one, it figures out how to force that wedge farther open until you find a crash that you can exploit. And AFL has been pretty successful. If you look at if you look at Michael's web page, you will find a huge laundry list of projects that AFL has brought to its knees. Stuff you and I use every day. So how did we do? How many bugs did AFL find in our Hammer implementation of DNP3? 1. There was a single bug. We had the set jump that we saw earlier, with the comment that talked about out-of-memory exception handling. Yeah, we kind of forgot about that. Like, it didn't immediately occur to us. Oh, wait, what happens if there's just some ridiculously long message that ends up exhausting our resources? Well, we were talking about totality earlier, right? So an exception is a partial function. A function is total if for every input there is some output. And if instead you end up with bizarre undefined behavior, escaping the context that you're in, you no longer have a total function. I totally just said that. So what the set jump does is if we hit an out-of-memory exception, we wind back, we clean up the resources that we've wasted, and the context is sane again. We've never escaped the context that we were in. So let's take a look at things that people have developed that go past what's going on here. So I said that speed was one of the goals of Hammer, and we kind of fell down on that. Hammer is actually really, really slow, and this is because it's basically interpreted. However, Jeff Coupry over in France took Rust, which has hygienic macros, and he realized, okay, so what Hammer's doing is, we've compiled a parser, right? You write a parser, you compile it. You're composing objects at runtime still. Like it creates the objects, it composes them together, and then it walks through them in much the same way that an interpreter does. And what Jeff realized is that if you have hygienic macros, you can instead have the macros generate the code which the compiler then compiles, and you end up with something orders of magnitude faster than what we were able to do with an effectively interpreted parser generator library. If you take a look at his GitHub repo, there are some benchmarks. They're very impressive. Nom is pure recursive descent, but honestly, between Rust being zero copy and macros to code to machine code, it's fast enough that it really doesn't matter. And the thing that makes me super excited is that Nom is actually starting to see adoption. At this point, I basically treat Hammer as kind of a reference implementation of interesting things you can do with systems, languages, and parsing. Nom basically takes the good parts and turns them into something production worthy. It's at 1.0. We're going to be seeing Nom-based parsers in VLC soon. Cross your fingers. Other projects that are moving to Rust have started to use it, and this is basically the best thing in the world to me because it means that the kinds of parsing vulnerabilities that have been plaguing us for decades are finally going to start to disappear. So another thing that Sven Halbert did, I kind of dared him to do iter-ATs in C, and he did it. So Oleg Koselyev came up with iter-ATs in order to be able to process streams in a composable fashion. The idea is you have this enumerate that presents either some data, or there's not any data at the moment, or there's not going to be any more data ever. It presents that to an iter-AT, and the iter-AT does something to it, and then sends back either stop with some return value, or continue, like send me more data, or if something went wrong, it returns an error. And this is pretty great because it lets you get complicated with how you parse things, and you don't want to write things to be complicated, right? But standards bodies do this all the time, like XML. XML lets you use all kinds of different encodings, and so the very first thing you see is what kind of encoding are we going to use, but then you have to switch off to whatever's going to do it. And yeah, I suppose you could do it with like switch cases and stuff, but that's massively ugly. Instead, however, if you can compose iter-ATs, you can, the first iter-AT will make the decision of, okay, well, who gets the rest of it? And you don't have to like set up more state or anything. It picks up in the stream where it left off. And in C, he implemented word count. It's faster than the standard Linux word count, just by using functional programming. All right, so this has been kind of a whirlwind tour, and I can't believe it's already been 50 minutes. But a few things to take away. The world is not going to expect a lot out of you. However, we can do better, and we should. If we don't do better, code is going to keep being terrible. But we can use the idioms that we've been celebrating here, even in languages that don't natively support them. Normally, we appreciate it when a compiler does this. Compilers do all the ugly, messy work that we don't want to have to manually do. But if your compiler is not going to be able to do that for you, you can do it yourself. The way to do this is to figure out what your semantics need to be, and then write so that you know what all the cases are, and you don't have to worry about edge cases. So what are we going to be doing next? There are lots and lots and lots of formats out there. There's lots of really old daemons that NTP is a wonderful example. The vulnerabilities keep showing up every day because this code has been around since before people really cared all that hard about what adversaries might do to it. Right now, we're really only able to handle batched input streams. Bind kind of obviates the need to have an input stream of tokens the way that you can have in Scala, but that might be neat. Incremental parsing is really the big one there. Like NOM can do incremental parsing. So if you have like just a stream of data that's not complete, you can hand it to NOM and it will take care of it. Error reporting is awful. All parser generators have terrible error reporting. I really don't have an excuse here, I'm sorry. This is the really exciting one. So I was thinking like, okay, Antler's pretty great. I love All-Star, I use it all the time. Maybe I'll implement that one next. And then Daniel Spivak walks up to me today and says, hey, did you hear about Matt Might's extension of Berzozovsky's derivative to the context-free languages? So Berzozovsky's derivative on the regular languages is kind of an old, mostly of historical interest way to do regular language parsing. A couple of years ago, Matt extended that to the context-free languages, and it was awesome, but it seemed like there were pathological cases. And just the other day, one of Matt's postdocs figured out that it is cubic. This is getting implemented. It's really getting implemented. Another thing I plan to implement. So I mentioned that that Hammer is slow because it's effectively interpreted. However, LLVM is totally a thing, and it is a thing with an API. So Packrat has no compile function, but we can basically do the same thing with Packrat that we're doing with the regex VM. The regex VM just assembles a bunch of instructions, right? There's absolutely no reason why we can't assemble a bunch of LLVM instructions and then JIT them. I'm not really sure whether it counts as a JIT. I mean, it's kind of like just-in-time assembly or kind of like ahead-of-time assembly, so I'm calling it slightly ahead-of-time assembly. And finally, let's just get rid of C already. Because, I mean, TQ and Sven and I did this mostly just to prove we could. And all right, we've proved it. I'm very tired now. Let's move on to Rust and other systems languages that are actually worth our time and do all the work for us. So, if you are interested in language theoretic security, we have a mailing list. We talk about Hammer there. We talk about other LangSec things. Code is in the repo. I'm on Twitter. Please feel free to contact me about any of this. If you know LLVM really well, I would love to talk to you today or tomorrow. And I think that's all I got. Any questions?